All right, a very good morning, students. In the very last class, we have just started our new chapter, that is chapter number 2, Structure of Atoms. In this particular chapter, we have just studied some basic concepts like the atom was not only the main constituent of the particle. In spite of that, there are subatomic particles like electron, proton, and neutron. And also, we have just a little bit studied about them, that how the scientists discovered electron, proton, and neutron. Rather than we just studied Thomson's model of atom, which was anyhow after some time was rejected. Now today we are going to study our new topic, that is Rutherford's model of nuclear atom. Okay, Rutherford's model of atom. As the Thomson model was studied, same as it is Rutherford model is studied, and it was much successfully explained by the particular scientist, that is Rutherford. Now, how did he explain about this and what are the concepts behind this? Let me start with this. All right. Okay. So Rutherford's model is also known as alpha particle scattering experiment. Alpha particle scattering experiment. Why is it so? Let's start. See, Rutherford took a source of alpha particles. In the last class, I just told you a little bit about what are the alpha particles. I told you that there are many radioactive elements in this earth which are unknown to scientists yet, which are unknown to everyone yet. Yes, yet the some radioactive substances we know, they emit three different type of radiations known as alpha, beta, and gamma. Alpha is basically of positively charged, beta is of negatively charged, and gamma is neutral. Okay, so Rutherford took a source of alpha particles. He took any kind of radioactive element which was emitting alpha particles in ease. So what did he do? He took a source of alpha particles which emitted alpha radiations, and then he put a lead plate, just to make a hole. It was just it was nothing. It was just to make a hole so that the all particles, all alpha radiations were emitting smoothly. After that, what did he do? He put a gold plate, a little gold plate, which was coated with zinc sulfide screen. Now, what was actually happening? When he started applying the alpha particles, when he started releasing, what happened? When the gold particles, it was the gold plate, when the gold plate was struck by these alpha radiations, what actually happened? Most of the alpha particle rays are going smoothly, effortlessly, without any tension, without any stress. They are going very easily. Okay, and some of these alpha particle radiations, after striking on this gold plate, were deflected by some angles. These were deflected by some angles, and only a few radiations, almost 1 out of 2000, were reflected back. That means when they strike on the gold plate, they deflected back. Okay, so these 3-4 observations were observed by Rutherford, and he thought that this is almost, almost surprising, almost amazing for him, because according to him, according to that time, only Thomson's model was in the mind of scientists. So the scientists were thinking that the whole our atom is made up of positive charge and electrons are somewhere embedded in it. Like I have told you, it was a watermelon model of Thomson. So according to him, the Thomson model is totally wrong. And since the most of alpha particles are going effortlessly, going smoothly, that means the most part of the atom is empty, it is hollow. First point. So first observation according to Rutherford after this experiment was that most of the part was empty. Just a second. Most of the part was empty of the atom. Secondly, he said that since some alpha particle radiation are deflected by some angle on striking with gold plate, that means there must be a repulsive force. It's quite simple. If the alpha particle are positive charged, okay, and after positive charge is striking and not going smoothly, it is deflecting. That means it is attacking, it is reacting to a positive charge particle. Only after that it is deflecting. Am I clear, or should I repeat it again? Okay, let me repeat this particular point again. When the positive charged particle, after striking with gold plate, deflected, that means there must be a kind of repulsive force. And you know very well, you know it from 7th, 8th class, that positive charge repel positive charge and positive charge attract negative charge. You know that very well. Okay. So that means if there is positive charge already somewhere, only then these radiations are getting deflected. Okay. So according to him, there is something positive charge, but this is somewhat densely concentrated. This is not completely embedded, as Thomson said. So that was wrong, according to Rutherford. The positive charge is densely concentrated, and after some time, he said this positive charge, densely concentrated part, we can say sphere, and he named it nucleus. He named it nucleus. That you know very well. You know very well about the nucleus. Okay, so this was the main important observation. Third point, he said that only a few particles were getting back. After striking with gold plate, only a few particles were getting back. Why is it so? According to him, this 180-degree repulsion quite may be possible due to electrons over there. Okay, so Rutherford, after these 3-4 observations, explained that first one, our atom is mostly empty, mostly hollow. Second point, that there is somewhere a positively charged, densely concentrated sphere known as nucleus. At point, one point I should add, he also explained that this particular sphere, this particular nucleus is very small as compared to our whole atom. Okay, he said that the radius of this nucleus is as small as we can assume like a cricket ball, and our atom is of 5 kilometers. Okay, so according to him, our nucleus is just like of a cricket ball, and our whole atom is like a ball of 5 kilometers. So these two particular important observations were given by Rutherford. Okay, and lastly, he gave also an important observation about electrons. He said that electrons are around this nucleus in some circular path known as orbit. He said that our electrons, suppose this is our electron, I'm putting it negative charge, are somewhere, but in, let me explain this very well. This is a kind of nucleus, and our electrons are revolving around it in circular path known as orbit. Okay, so this Rutherford model also reminded us of solar system. Like the nucleus is our sun, and the electrons are moving in their orbits like planets. Okay, and he also explained that these electrons and the nucleus are maintained, are neutralized by the electrostatic charge. So these three important observations, according to Rutherford, were given to us, and which was quite liable, quite important. So Rutherford was quite successfully explained all these things, and which we still use, these important postulates we still use in our daily lives. But after some time, as the scientists keep growing, same as it is, Thomson model was rejected, same as it is, some drawbacks were found in Rutherford's model too, which we would explain later. But right now, since all these points have been cleared, we are going to our next topic, that is atomic number and mass number. All right, student, till now, if you have any doubt, please tell me. Then we are moving to atomic number and mass number. Clear? Okay. Now next move to our next topic, that is atomic number and mass number. Now what is atomic number and mass number? See, Rutherford has told us that there is nucleus, there are electrons, there are protons, neutrons we have already known about. Chadwick has already told us, a scientist Chadwick. So after these all observation, and we also came to know that our atom must be neutral. Their stability must be neutral. That means number of electrons, number of protons must be equal, so that positive and negative charge is balanced. So our next topic is, what is atomic number, mass number, and after that we would study what are our isotopes and isobars. Okay, atomic number is quite simple. It is defined as the number of protons in an atom, or we can say number of electrons in a neutral atom. So atomic number is defined as, so denoted as Z, and it is equals to number of protons in an atom, and we can say number of electrons in a neutral atom. All right. Okay. Now, what is mass number? We have known about the atomic number. See, atomic number mainly told us that there should be number of protons equals to number of electrons, so that our system, that our whole atom must be neutral, must be stable. First one. Okay. Second, mass number. Since atomic number was only based on electron or proton, only the numbers, the mass number was totally based upon number of protons plus number of neutrons. And after combining, this is also known as nucleons. So what should I say? Nucleons, proton plus neutron. Okay, and this is, mass number is defined as A. How should we find A? A equals to number of protons plus number of neutrons. Let's take a simple example, and you would quite easily tackle with this topic. Okay, we have in our book bromine. We have bromine. Okay, one point I think you know about since 10th class, but I should tell you that our mass number is denoted in the lower subscript, and our atomic number, atomic number is denoted, is put in the lower subscript, whereas our mass number is put in the higher subscript. Okay, so let's take an example. We have 8035 bromine. Now, in this, we have to tell what is our atomic number, what is our mass number, what are the number of protons, number of electrons, number of neutrons. Already we know that this lower subscript Z is denoted as atomic number. First point. And atomic number tells us that there should be number of protons equals to number of electrons. So that means we can say Z is 35, number of protons equals to 35, and number of electrons is also 35. First case. Second, we have to calculate number of neutrons. So how can we calculate number of neutrons? We know that our A is proton plus neutron. So A equals to proton plus neutron. A is 80, proton is 35. We can easily calculate neutron. Neutron is 80 minus 35. Am I clear? This simple concept will make you that how can we calculate our atomic number, mass number, and with the help of this, we can calculate our number of protons, neutrons, and electrons. Okay, all right. Now we are going to move our next topic, which is also based on electrons, protons, and neutrons. That is isotopes and isobars. What are the isotopes and isobars? as we have known about the number of protons, number of neutrons, number of electrons, so isotopes and isobars what came into, you can say, came into existence after some time. See, our universe is so abundant. There are so many elements which have different type of number of protons, neutrons with the same particular atom. Like if I'm talking about isotope defines as the atoms which have same atomic number but different mass number. What I'm saying, that have same atomic number but different mass number. So isotope and isobar. Isotope, isobar. Okay. Now, what does isotope define? Isotope is same atomic number but different mass number. Whereas isobar is just reverse to it, which explains same mass number but different atomic number. All right, students, sorry. Now you should have a query, because I have query right now. Tell me something. If we are talking about isobar and isotopes, which should explain you same atoms? See, isotopes tells you that there should be same atomic number. That means this lower subscript, that I'm putting it X. Okay, that means this lower subscript must be same of both the atoms. Should X and Y must be equal, or in isobar they should be equal? Let's find out. Okay, let we have example of hydrogen. Quite simple. In hydrogen, we have 1 1, since we are having same atomic number, and you know very well, and this one. These are known as isotopes. This 1 1 hydrogen, 1 2 hydrogen, 1 3 hydrogen, these three are known as isotopes of hydrogen. Okay, that means the atom is same, but due to different mass number, due to change in protons, due to change in neutrons, so not protons must be same, due to change in neutrons, the isotopes are getting changed. Okay, and also we have named them very differently. This is known as protium, this is known as deuterium, deuterium, and last one is known as tritium. I hope you have reminded that you have heard about these topics. Okay, and also important point is, the most abundant element is 1 1 hydrogen rather than deuterium and tritium. If this is 99% in our universe, these two are found as 1%. Okay, so these are isotopes. Now let's take an example of isobar, which are having same mass number but different atomic number. Okay, let's take an example of nitrogen and yes, carbon. Okay, now you know that carbon having 6 as atomic number and it has 12 as mass number. Same as it is if I'm talking about nitrogen, it has 7 as mass number and 14 as atomic mass. But as the hydrogen have isotopes, same as it is, carbon has also isotopes. 12 carbon, 13 carbon, 14 carbon, so on. Almost 40, not more than 40. These isotopes are rare, quite obviously. And the most importantly, these 13 carbon is so important. This would you study in your high classes. So let me take 14C and 14-7. These are known as isobar. Same mass number but different atomic. Okay, this was all about isotope and isobar. How much time are we left? Okay, Now the topic is covered. Now I told you that our Rutherford's experiment was quite successful, but as usual, it has some drawbacks too. We would discuss these drawbacks and then we would introduce our next topic, and the next topic we would start in our next class. Okay, so Rutherford's model was quite successful and it explained us too much. It explained us about the nucleus. It explained us about the, you know, electrons, orbits, and also told us that the nucleus is so small to the total atom. It's like a cricket ball into a 5 kilometer ball. Okay, all these observations, and also he gave us a rough idea that this is quasar nucleus and electrons are revolving around it. So he was quite successful according to him. He was quite sure that he has given all the points. But what happened after some time, there came a scientist which was known as Maxwell. According to Maxwell, Maxwell was a physicist. He told that according to moving electrons, according to moving circular things, there is an theory known as electromagnetic theory, which explains that if the small moving things keep moving, small spherical things keep moving, after some time, they start losing their energy. So according to him, he said that when electrons are getting moved, after some time, what would happen? These electrons and the energy in which they are moving, that is the orbit, they would start losing their energy. And what would happen? The orbit would losing its energy and it would shrink. That means it would start really disappear after some time. So this was the first drawback which Rutherford could not explain. Secondly, he did not explain the overall stability of whole atom. He told us that there must be an electrostatic attraction between the positive charge and the negative charge, so that our atom is whole, stable, and neutral. But he did not explain that if these are moving, the orbits could be shrink. First point. Second point, Rutherford said, if is it so, let us assume that our electron is stationary. He said that let us assume that electrons are stationary. They are fixed at a position. They're not moving. So another scientist came and he said that if electrons are not moving, what would happen? This positive charge would keep attracting it into it, and the electron would jump into it and they would die after some time. So this was not also explained. Okay, and third point, he did not explain what actually orbit defines us. Okay, so these 3-4 points were not explained by Rutherford, known as limitation of Rutherford. Okay, and due to these limitations, Rutherford's experiment, which was quite reliable, was rejected after some time. But Rutherford's model was further modified, and it was after modification gave another name known as Bohr's atomic model. Which we would study in our next topic, next class. So Bohr's atomic model, I have just given you a brief idea. Why do we need to study that? And another point, when we need to start Bohr's atomic model, another scientist came to know about the dual nature of our light. That is, it has particle, also it has wave nature. Okay, what I'm saying, that as the Bohr was explaining Rutherford's model, it was improving it. On the very same time, another scientist came to know that light has dual nature. Light, that you know, it has dual nature. That means it has particle nature, also it has wave nature. Okay, so after some time, these two concepts were merged and we came to know about another theory that we would start. Okay, so this was all about today's lecture. We have studied about Rutherford's model. We have studied about its drawbacks. We have studied about isotopes, isobars, atomic number, mass number. If you have any kind of doubt or query, you can ask me. Sir, can we unmute our students? Students, if you don't have any query, you don't have any doubt, any particular topic, Rutherford's model, or atomic number, mass number, isotope, isobar, something. All right. So in the next class, what would we study? Let's have a brief introduction, as you're not having any doubt. I think I have explained very well. You don't have any doubt. Okay. Topic, we are going to study about developments leading to Bohr's model. First one, second one. First one is dual nature of light. That means both has particle as well as wave nature. And second one is atomic spectra. Today we will start with atomic spectra. Okay, so I won't have a recapitulation in tomorrow's class. We will just start with atomic spectra. Why do we need to study atomic spectra? Okay. Students, if you can ask, please ask what are your queries or doubts, something. Because I have explained according to by my side. And the next topic, we don't have much time that we will start the topic. Or should we end the meeting? Sir, I think we should end the meeting.